there are a couple of prerequisite things we need to just show you. It's some stuff that maybe I guess in the American curriculum they've already done, so when we hit calculus you won't have any idea that this notation means unless we sort of talk about it before we go. So here's an example of like what you do in real life. There is a way to model it in math. So for example, let's just say that if the temperature is less than 10 degrees, like it is this morning, or this afternoon I guess, what kind of clothes might you be wearing? Jacket. Incidentally, this does not always work for the ladies who, for some reason, tend to wear shorts no matter what, or you know, short sleeve shirts no matter what time of year it is. I see them on my drive to school, freezing in the snow, and they still wear shorts and anyways. But let's just say practically, I see. Yeah, but you got a coat on, so it doesn't count if you have a coat. You might wear like jeans, right? Something else like that. Jacket and a jeans. What if we're somewhere between, I don't know, 10 and 20? Like, this is probably where it's reasonably getting like t-shirt weather. Maybe maybe in this one we say let's do t-shirt and jeans. You're probably not going to wear shorts just yet, but you'll probably get away with the t-shirt. And you know, if we're over 20 degrees Celsius, you know, you probably have t-shirt and shorts. We can argue about where the cutoffs are, but right, this is just something, you know, like practically, you look outside, you know what the weather forecast is going to be, you make a decision about what you're going to wear. So as a function, here's how it looks if we write it, is we go, this function on clothing, I use a big brace like this to say, I have a whole bunch of pieces, they all belong to the same function. The first piece is jacket and jeans, and then I say when it's going to happen. So if it's a function for the temperature, which in our case is x, I would go when x is less than or equal to 10. And if it was like t-shirt and jeans, this is when I'm between 10 and 20. And then finally we said t-shirt and shorts when we were over 20. So piecewise graphs, sometimes we model something and it behaves one way up to a certain point and then the function changes. So we can use a piecewise graph to describe the pieces of a function. One that you've been doing a lot with is the absolute value function, and that's not very convenient for us to work with because I'll just see if your math teacher did this to you. How do you describe, what does the absolute value function do? Yeah, the most common answer I get is it throws away the negative. So how do you mathematically make a nice tight definition that says throws away the negative? It's very difficult, right? So how do you come up with a nice tight definition that says the absolute value? Well, this is what it would look like as a piecewise function. The absolute value is just x whenever it's greater than or equal to 0, meaning you don't do anything because it's already positive. What do you think I would do to this if it was negative? Yeah, if I make it the negative of x, then a negative negative brings it back around to positive. So this is the piecewise graph of the absolute value function. And now I have a robust definition. Depending on whether the value is negative or positive, I know which piece of the function I'm on. Okay? So why don't we try this next one? Can we write x minus 5, the absolute value of x minus 5, as a piecewise graph? I'll let you guys try it. I'll give you like a 30-second head start because it's brand new. I know you may want some help with it, but see if you can do it. So this is what the piecewise graph looks like. It's the same as we did before. You have x minus 5. This is what we started with. It doesn't change as long as the number that comes out is positive. So as long as it's greater than or equal to 5, this piece will be positive. That's okay. But if we go less than 5, that means it's going to be a negative. So I have to put a negative in front of the whole thing. So this would be a piecewise definition of absolute value x minus 5. Okay. So we'll try a graph here that I've given you. And especially in our first unit on limits, you're going to see these a lot. So don't worry if you're just sort of rusty at it. It's not something that you're going to never see again. We'll practice it a lot. This first one, it says when x is less than 1, you're the graph 1 minus x. So here's where my pieces change. You don't need to do this little dashed line that I'm putting in there. But while we're starting, I'll put it there just to help you remember. That's where things change. So on the left side, here's the left piece. It's going to be 1 and the graph is minus x. So it would go like this red graph. And this is the right side here. And this one is the square root of x minus 1. So it's going to look something like this purple graph. So there's the two pieces. I sketch the left side, sketch the right side, and then I'm going to use the graph to evaluate x equals 3 and x equals negative 2. So what do you think? If I use the graph, what's x equals 3? What's the value going to be? Yeah, so here's x equals 3. There's the value. So it will have this one. It's hard to pinpoint, right? What would it be if you use the function? Can you figure it out? Is it the left side or the right side that I'm on? I'm on the right side, yeah. And the value of x is? Yeah, so since it's a value of x is 3, I'm going to put this in as root 3 minus 1. So root 2. So here this would be the value root 2. So we should be able to do this both ways, meaning if I take a look on the picture, and I should also be able to take a look here and plug it in using the numbers in its definition. So what will I do at x equals negative 2? What will the value be? Yeah, it is 3. So here's, maybe I'll do it in blue. Here's negative 2. So this is where I find it at the point x equals 3. Or sorry, y equals 3. And if you weren't wanting to use the graph, you're on the left side. So it's going to be this guy that you use. You're going to be using the value 1 minus negative 2, which is 3, just like we found on the picture. Okay. Now this certainly is not a necessary thing for you to know. It is just a nice thing for you to know. So I'm going to show you how to plug in one with your TI-83. Your TI-83 is a great, or any graphing calculator you're using, is a great utility to help visualize what we're doing. One thing is that calculus is really good at, and what I recommend that we'll get in the habit, you'll notice I do a lot of pictures in this course, is because the algebraic is very hard to understand sometimes. It's very conceptual, whereas the picture is more, it illustrates things better. So using your TI-83 can help you out a lot when you get stuck. So you can see what's happening in the pictures. So you need to bring up, I'll bring up mine. And we're going to make this piecewise graph I have here. So if you don't know where the absolute value graph is, you go math, and then you go over 1 to number, and it's that one here, so it's the absolute value that I want. So the first one I'll put in is absolute value of x. And then the other one I'm going to put in is x minus 1. So you could go ahead and look at it even right now, and you get one of the graphs and the second graph there, right? So we don't want to see them at the same time. You can kind of just, it says that x equals -1 is where they change. So you could, just blank one side out when you're looking at it. But what I'm going to show you is how do you force the calculator to just do the parts you want. What you need to do is you need to put some brackets around what you're going to do. So I'm going to put in brackets here. And I'm going to use the test, not like make you nervous test, like as in right there it says T-E-S-T right above math. So second function test. And there's where all your inequalities are in the calculator. So if I only want something to happen when x is less than -1, that's what I'm going to put here, x, and I'm going to ask for it to test that it is less than -1. So I'll do it one more time on the other graph with you. I need to put brackets around it, otherwise it'll only test the piece that's right next to it. And it's going to be when x is this time greater than or equal to 1. So I'll go test greater than or equal to -1. And now you see it stopped graphing. Oh, there's the other one. Now the only thing that your graph does that's kind of weird is it's actually connected the dots here. You see that line? Be aware, if your calculator is in that setting as well, that line does not exist on the graph for real. It's just that the way it plots it is that the dots are all connected in a sequence. I think there is a setting so that you don't have to connect all the dots, and then this would appear empty. But as far as I know in my calculator when I do it, maybe because, I don't know, maybe there's a better setting than this one, this graph is not very Oh, okay, actually it worked. There we go. Okay, well it's not connected there. So that gap should be in the picture. All right. Again, it's not a necessary thing. If you didn't know how to do that, you would just plot them in, as I said, without this little test feature. And that way you just have to blank out half of the graphs as you look at one side and the other side. But, why not? It's there. You can use that now where it's appropriate. All right. So we briefly talked about what some of the problems in calculus are. Today, one of the things that we're going to look at, which is interesting, is this first thing here, x squared minus 1 over x minus 1. Now, can you tell me what the value would be at x equals 1? Undefined. You're sharp. Why is it undefined? Divide by 0. Well, I'm not nearly as smart as any of those guys who did the stuff before me, but they were kind of clever in that they said, well, it is and it isn't. Let's take a closer look. And that's what we're going to do today. One of the interesting things that happens here is the rules for division are pretty well defined. Like if you go 5 divided by 0, yes, that's undefined. But what is happening here? If you plugged it into your calculator, what would it be? Something divided by something? Yeah, we could rearrange, but in this case, maybe I'm just not being clear. It's 0 over 0. So what happens when you divide 0 by 0? Well, there's some interesting stuff that happens. We'll even look at some interesting stuff that happens when we say, well, what's infinity divided by infinity? So let me show you, this will give you an idea where we're headed today. Let's look at the picture. The picture of that graph is x squared minus 1. And I'm going to make sure that I can see it at x equals 1. So because I'm trying to illustrate this to you, I'm going to change my window. So my window, I'm going to go from like -2 to, oops, sorry, I don't need to go from -2. Let's go from 0 to 2. Ah, so do you see what the calculator did to cheat? Can you see right there? They blanked it out. Your calculator doesn't do calculus, unfortunately. It only took grade 12 math. So there's a hole in the calculator there, right? Because the calculator knows it's not supposed to divide by 0, so it skipped that part. But can you see, like, what if we zoomed in really close? What if we said, well, let's just pretend. I'll move this. Zoom in. It's not such a scary graph. It's just that there's a hole in one spot, right? It's just this one particular place. So the way that we kind of say yes but no is we're going to look for very, very, very close values. Okay? Like if I'm very, very close on this side or I'm very, very close on this side, it looks like they kind of think it's the same piece. All I'd have to do is fill this dot in with my pencil, right? And those are some of the interesting things that we will look at. It lets us do things which you wouldn't think are otherwise possible. Like, for example, if this is your, well, I don't know why fruit flies would be, maybe they're interesting to you. Apparently the person who wrote your textbook, it was. But they're looking at the population of fruit flies over time. And what we can do is, if we connect the line like they have here, this gives us the change in fruit flies in 22 days. So it's telling you that 192 more fruit flies are there, and that happened over 22 days. So the average rate of change is 8.6 fruit flies per day. But if you look at what's happening, there's a lot more fruit flies over here. You see, this slope is a lot steeper on this side than it is when I get to this side of the graph. See, that average is not very accurate except for maybe 1 or 2 places where I get close here to seeing that the slope is similar to 8.6. Now, how do you find a slope like this? If you were to go right there, the way you do it in the tangent problem is you start shrinking this thing to 0. And as I start moving those points together, what happens, I'll clear this up and zoom in on it, is as they get closer and closer together, the line that you can connect them with is starting to be more and more like this tangent line I was telling you about. But the weird thing is, the tangent only exists once we divide by 0. So now we're telling you we're going to teach you some of the rules for dividing by 0. Okay? And the rules, as I say, the rules aren't that bad. I could teach them to you in probably one lesson, but I want you to understand where they come from. So the tangent problem, this is the instantaneous rate of change. So whereas I'm showing you that there's 8.6 flies per day is the average rate of change over the 22-day period, you'll be able to say at any particular instant what is happening to that population. So on day 5, the change is exactly, and you can say it, for that one instant. The other thing the tangent problem does for us is it gives us the slope of a line. Tangent at a point. Now, as I told you, this tangent problem is like the first half of our course. We're going to build it up over a lot of time. So you're going to know this, but I can tell you right now, I'm going to keep repeating those 2 points to you for months because it is that important that you know about them. It's okay right now if you forget, but we're going to keep harping this on you. When you hear the word tangent, you have to think of a couple things. Now you can do instant rates of change, and you can see the slope at a single point. You don't need 2 points anymore for a slope. A secant line. Secant is a line through 2 points. So when you hear that word being used, it's just saying like every line you've done up until now. So here's the slope of a secant line. And they're trying to do the same picture for you. Of course, they're doing a much better job with computer graphics than I did. But this is the rise. This is the run, just like any other slope that you've calculated. So that's what you have here, the rise over run. And what they're saying is, right now, the run is this big. It goes from here to here. What I'm going to do is start making that happen smaller and smaller and smaller until eventually it hits 0, and we get this tangent line, which in this picture here is that one. That bottom line is the tangent line. Okay. So this is, of course, not our goal today. This is something we will practice, but you'll notice so far I've been using this word like shrinks or goes to 0. Been kind of hinting at what we're doing today, and that's what we're going to take a look at here, is what this thing is as called when we say limits. So when something approaches a value and doesn't actually touch the value, that's what we're talking about for a limit. And here in this context, when the run becomes 0, the secant line becomes the tangent line. So that's why we have to talk about limits before we can go over all the calculus rules. Has anybody done any calculus before? So, some people have done it like in other, like I think it was Singapore or something. Like I've had students who tell me, oh yeah, I've done calculus before, but they're at the same level as you are. Like they really don't know much understanding of it. They really just have been taught a bunch of quick rules for finding some of these things. So this process of going from this is where you are now, and this is calculus. This is how we get there is in this first unit called limits. Once we build up that concept, then you should have an understanding of how we got there. Okay, so here's the notation for a limit, right? Just so you know, now we're rewinding. This is where you should, that was an overview of some stuff. Here's where we'll start to hop on board with the course, okay? Course begins now. So here's the notation, and it reads as the limit as x approaches 3 of x squared plus 2x plus 1. Now there's some strategies to trying to figure out what a limit is. The first one is direct substitution. That means all I'm going to do is, if I'm trying to send the variable x to 3, why don't I just try doing that? 3 squared plus 2 times 3, whoops, excuse me, plus 1. So that'll be 9 plus 6 plus 1, which is 16. And that, in fact, is the answer here. The limit as x goes to 3 of x squared plus 2x plus 1. It's just 16. And you thought it was going to be hard, right? So when does a limit exist? Okay? This is the part where people start to then, this is a definition that you need to know. A limit exists. I'm going to give you the graphical one first because it's the easiest one to picture. So the limit will exist, and again, it'll make a lot of sense in the picture. I'll show you how to do the algebra later, because it's possible to talk about one side or the other. But when you can approach from both sides and arrive at the same value, and one important thing here is, and I'll do it in capitals, takes longer to write in capitals. It's not necessary that the function's defined. So you can't just say, it doesn't work because I can't substitute it in. This is the key difference between a limit and just substituting it in. For a limit, we do not require that you actually go to the value itself. So I think it's still queued up on my calculator. So here, you don't actually have to go to this value where the arrow is pointing. It's not defined there. Everything you've learned so far in math is still true. It is not defined at that point. But a limit is a new thing which says, but you don't have to touch that point. Instead, all you have to do is approach from one side, and this is where I would end up. Let me move the cursor there. That's where I end up if I approach from the right side. And if I approach from the left side, I also end up in the same spot. So for now, that's the definition we're going to work with. Basically, they both meet up, and you don't have to worry about whether or not it actually works in the middle. So let's try a couple together on the graph. So let's put these natural log of x minus natural log of 2 divided by x minus 2. And we'll use the graph to try and determine whether or not this limit exists. Oops. I'm going to have to... I missed a set of brackets, so natural log x minus natural log of 2. And we're dividing it by x minus 2. So the first strategy I said was direct substitution. It doesn't work here. You can't stick in x equals 2 because you divide by 0 on the bottom. So you can't use the first strategy of just see if it's defined. Just plug it in. So what we're going to do instead is try and use this first definition that I gave you, is that we're going to look at it from both sides and see what happens. So we're going to make a good window. 2 is the number that I'm concerned about here. So let's try maybe like negative, or sorry, you don't need to go negative then, 1.5 to 2.5. And of course, you know, hopefully this is enough to get the picture on the screen for the y values. Oh. Okay. So in this particular instance, you see I've got this hole in the graph, but do they meet up as they approach each other? Yeah, they do meet up as they approach each other. This limit does exist because as I move my, if you follow the arrow here from this side, where I'm ending up is the same place as when I approach from the other side. Okay? So the limit does exist, and if we wanted to know what the value was, what you can do is you can trace it out and see what happens. So right now it's saying, yo, you can't do anything at x equals 2, it's not defined. But as I approach, see, I'm moving over from the right side, and I'm getting, I don't know, maybe like 0.5, and it's about 0.5 here. If I had to make an educated guess, that would be my guess as what the value is as it passes through. He's getting closer and closer to 0.5, undefined at the point itself, but it's still closer and closer to 0.5 as I pass through. So that would be my educated guess using the graphing calculator. That this is 0.5 is the limit. Okay, so same question goes to you now. Is it defined? If it is, just substitute. If not, we're going to try and use the graphing calculator to figure out what is the value at x equals to 1. So here's the picture that I'm working with. And again, aside from the fact that there's a hole in the graph, it's a nice smooth curve. Both pieces connect except for the hole that's been chopped out of it. You can also, as I said, use your trace button and walk across it. So if I had to take a guess here, 2.1, 2.08, 2.06, 2.04, 2.02, and 1.98. What do you think was the value in there? Yeah, if you're not satisfied, you can zoom in more and get a more accurate answer. The more you zoom in, we'll zoom in again. The more it will get closer to what we're trying to find here. So, see, now it's 2.005, right? And oh, it even seems like my calculator went and took some calculus in the meantime, because right now it's saying at x equals 1, the value is 2. And then here it's 1.99. So if you're not sure about how accurate it is, just zoom in more on your graph. But yes, I would say the limit does exist here, and it equals to 2. Okay, there's another technique which is good, and it's the table method. So we're going to take a look from a table of values, and we're going to start by putting in this function here on the left. Okay, so once your function is in, what we want to do is we're going to use the table method. But before we do that, we're going to go to table setting right here, table set. And that second function window, you want to make sure that it lets you ask for the independent. Otherwise, it tries to fill in the values for you, and it may not pick very interesting places to look. So make sure you move the independent to ask. And then I'm going to go to that table, and it's waiting for me to plug in a value. And what I'm interested in are values near 0, because I want to know what's happening. So if we were to think about this as a graph, okay, what do you think? What side of my graph am I on here? What side is this? Yeah, it's the left side, because they're all less than 0. And this here would be the right side, because they're all greater than 0. So let's plug some of those in. I'm sorry, I should have a should have a negative there. Negative 0.1. I'll plug in negative 0.01. And then negative 0.001. What does it appear is happening on the left-hand side? Where is it getting very close to? Yeah, it looks like it's getting close to 2. Now we're going to jump over. We don't want to touch 0 because we know that's not defined at 0 itself. But this gives me a bit of a picture of what happens as I pass through. So right here where the mouse is, that's the middle where it would be at 0 itself. And yes, those values, they're approaching 2 on both sides. So the limit exists. Even though you could not ask for what the value at 0 is, it'll still give you an error if you ask for it right there at 0 itself. So here, the limit would be 2. Okay, so this time, use the table of values to try and find what's the limit for sine of x over x as x approaches 0. The one that we're looking at, I think the only issue I ran across was that you needed to be in radian mode as long as it was in your calculator properly. So sine of x over x, I think it will even work in this one if you're in degree mode. You just won't get the same set of values. Now, where were we? Table. So here's the values that come up, right? And it's so close to 1 that it's actually rounded it for me. It's not actually a value of 1 there, but the calculator doesn't have enough decimal places to do that. It just rounded it to 1. So you can actually see this time the limit actually hits right in the middle there. As I go from the left, I approach 1, and as I go from the right side, I approach 1. So in this case, the limit is in fact 1. All right, so we've talked about when the limits do exist. Let's talk about now what do I mean when I say you have to approach from both sides and it doesn't have to be defined in the middle. Here's what I mean when it does not exist. This first graph here, if I approach from the left-hand side, the limit would tell me its value is 0. But if I approach from the right-hand side, it's telling me the value is 2. they do not agree, the limit does not exist. In this example, we would just say does not exist. Now, a limit has to be a number. It can't be something like infinity. It's very tempting to say the limit exists, the limit is infinity. Now, that's very close to what we want to say. We would want to say the limit does not exist, it's infinite. Because in this case here, they're not going to any particular value. There's an asymptote in this graph. And even though I'm approaching infinity on this side, and I'm approaching infinity when I come from the other side, that's not a place. Infinity is when you keep walking, right? If I wanted to send you to the number 10, I can get you there on a number line. If I want to send you to infinity, that's very mean. It just means keep walking and never come back. So when you're doing limits, in this case, yes, they both agree, but they agree that it does not exist. It's infinite. There will be a day we will discuss more specifics about, what you do when you deal with infinite limits, but in this case, they fall under the category of does not exist. And then the last one that can happen is the oscillating. This one is not one you're going to encounter frequently. These two are the ones that you're going to see and have to deal with lots. But the oscillating one is interesting. I'm going to pick some choice values here, and let's see here. Anybody remember what sine of pi over 2? Okay, what's the sine of 3 pi over 2? So I'm going to use this idea of 1 and negative 1 to show you how this graph does not exist for the limit. Okay, so I'm just going to start fresh, but this is the idea, okay? What happens if I use, this is the function, what happens if I use x equals 2 over pi? 1 over x is pi over 2. Sine of pi over 2 is 1. Okay? The next value I'm going to pick for you is going to be 2 over 3 pi. So its reciprocal is 3 pi over 2. That means the sine of 3 pi over 2 is negative 1. Which one's bigger, 2 over pi or 2 over 3 pi? Yeah, this one's bigger right here. So this is a smaller value. I'm going to pick another smaller value. So its reciprocal is 5 pi over 2. The sine of 5 pi over 2. Do you know what that is? It's 1, yeah. So I'll do one more, and I'll see if you can get the hang of what's going on in this limit. Seven pi over 2, what do you think? Even those of you who are rusty on trig should be able to pick this pattern out now. Yep. What's happening in each of these is I'm shrinking as I go down, because you see that denominator keeps getting bigger. It was a 1 when I started, right? 1 pi, 3 pi, 5 pi, 7 pi. The top is fixed. So this is actually approaching 0. The points that I'm choosing, eventually if you keep doing this pattern on and on and on and on and on, you're approaching 0 when you go along this pattern. Somewhere in there will be like 2 over 1,000,001 pi, right? That'll be a very small number. So these are approaching 0, and what happens as I approach 0? 1, negative 1, 1, negative 1, 1, negative 1. It keeps bouncing back and forth and back and forth. The closer you get to 0, it keeps bouncing. 1, negative 1, 1, negative 1. It keeps bouncing and bouncing and bouncing. That means nobody agrees on where they're headed in this graph. It's just going to keep bouncing up and down forever. So that's an example of one where it wouldn't exist. It again is more of theoretical interest. It's not something you will encounter a lot, but that's one way someone could prove a limit doesn't exist. Okay. So we've been just talking about graphically and tables of values. That's enough for us to survive today. And algebraically is where we're headed. So let me bridge the gap and show you where this worlds meet. Here's a funny graph. Without a piecewise graph, really hard to do. Okay? But for now, let's just go and use the calculator. We'll let the calculator do the work. So in y equals, it would be the absolute value of x divided by x. And this one, I'm going to want to do it oops, sorry. Don't need that bracket there. I don't know what my my window's not very good. Sorry. I'll have to. We're looking at the limit as it goes to 0. So I'm going to pick something where I can see x equals 0. So let's go from like -2. Well, the picture there goes from -4. So we'll go from -4 to +4. And the picture goes from -2 to +2. So I'll do the same thing. All right. There. Prepare to have your minds blown. Whoa, what just happened? All right. Important question. If you're on board so far, does the limit exist? No. Oh, thank God. Okay, you're all calculus geniuses. So as I approach from the left side, what's the limit from the left-hand side as I move here? -1. And from the right-hand side? 1. They're not the same, so the limit does not exist. So here's my picture. And I could say does not exist. Do you remember how we described the absolute value function before? I hope so. It was only like 20 minutes ago. This new piecewise graph, right? Do you think you could write that as a piecewise graph? Do you think you could do that? The problem is going to happen at the same place where we would split this graph. What do you think? If you actually can do it, you're going to go, oh, that's why the graph looks the way it looks. Can anybody enlighten us? What do you think?
It's x over x and minus x over x.
Genius. That's how I split up the absolute value. When it's negative, I multiply by -1. And when it's positive, I don't do anything. So this function really looks like this. 1 when x is greater than or equal to 0. -1 when x is less than 0. That's the simplified version, right? So now with algebra, I can show that the left-hand graph, the limit as x goes to 1 of f of x is the limit as x goes to 1 of +1. But the right-hand graph, oh, I'm sorry, this is the left one here. And this is the right one here.
Shouldn't the limit be x? I mean 0, x is 0.
It should, yeah. So that's just a constant. It never changes. It's -1. However, on the right-hand side, that right side piece, the limit as x goes to 0 of f of x, is just the limit as x goes to 0 of 1. And that's a constant, which is always 1. So algebraically, I can show you that the reason the limit doesn't exist is the left and right side don't agree. They're not the same value. Okay? Now, we will practice that a lot, so I know some of you are probably just like, wow, okay, I was okay with graphs and tables, but now my mind is blown. We'll get there, okay? But that's where we're going to be headed, is we want to be able to do it without having to always pull up the graphing calculator. The problem with the graphing calculator is it's a computer, and it doesn't always give you the best math answers because it has to round its values. So it may not give you the correct limit if you try to rely on your calculator. Of course, saying that, Stacy has a very fancy one that may actually do that. I don't know. If you have the TI Inspire, I don't know, that one probably has more complicated stuff than, it's about 10 years newer than the one that we're using. Okay, so it's time to check in and make sure that we're on board today. This is where you should be at if you understand what a limit is, okay? Here, I'm going to give you a picture. I'm not going to tell you what the function is. I'm just going to ask you questions about the limit. If you can do this, you're awesome. This is where you should be at the end of this lesson. Some of you may need to practice more tonight for homework to get there, but this is where we should be when we're done. So let's take a look. In this graph, g of x is the blue lines. Okay? I don't want you to call it out to me. I just want you to try and find these three limits, and I want you and your partner to look it over and see if you agree. There's always some confusion when we start limits because you're living in a world where none of this kind of idea existed before. Okay, so talk to your partner, talk to your neighbor, make sure you agree on your answer. If you can explain to your neighbor why they're wrong, you're already on the right track because everything in calculus will have a reason. If you know why they're wrong and you can say, hey, you made a mistake because, that means you're already on your way to the highest possible grades for the AP exam. Okay, so the one thing that you have to get used to doing in limits is you should not be going like this and looking at the value x equals 1 in this first one, because that's what you do in a function, right? And a function has, or a limit has more to it than a function. What's more important is that you be able to find the left and right side. Here's the left side as I approach 1. Here's the right side as I approach. That tells me about the limit. And what is the limit in this case? Yeah, it does not exist because those two did not meet up. They are in the different spots. Honestly, today, this will answer way more of your questions than anything else. If you're not trying to, visualize the two ends meeting or not meeting, that's so far the conceptual definition you have as a limit is it doesn't have to be between my fingers at the spot itself, but my fingers have to touch in order for the limit to exist. Okay, so think about it the same way. The next one, as it approaches 2, right, what happens there? The limit is 1, yes. They go together, and my fingers end up at the same spot. So here's what, so let's say that does not exist. So this one here, that one, and that one, I'm purposely trying not to draw the arrow right up to the dot because you don't look at the dot anymore. The dot is not important to us in limits. We only go from one side and the other side to see where we ended up. And in this case, we ended up at 1, so the limit is 1. Okay, the next one always messes people up because the dot has moved. There's a big hole in the graph. It's jumped up. This is just to confuse you because it doesn't matter what happens at the dot. Limits, what matters is that when you approach from one side, it's the same as when you approach from the other side. So in this case, I will tell you right now, this limit does exist. What do you think the value of this limit is? Good. Okay, I'll give you another minute to hopefully do this one a bit quicker, and then we'll talk up at the board. Okay, so if we head to -2, what's the limit? Good, it is 0. As I approach, here's from the left side, here's from the right side. They both hit at 0. What about at -1? Right, this time I go down this side, and I go this way. I hit at -1. And then what about at 0? Good, it does not exist because the dots don't matter. Remember, it's just where I'm coming from. And in this case, I hit -1 and +1, so this one does not exist.